Swayam Prabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 14. Just quick recap of the last module. We were talking about shrinkage allowance and machining allowance in casting processes, and we saw that the shrinkage allowance primarily because the casting needs to lower its temperature from the freezing temperature at which it has just solidified all the way to the room temperature, and there is going to be a coefficient of linear contraction because it is a metal. And so therefore, normally an allowance is given to the pattern, so that eventually after the contraction the casting can be of the size which is desirable. And also I shared with you a table where we talked about the various materials, the various shrinkage allowances, and the more important machining allowance which is used because the casting has to now get into the assembly into a certain assembled machine, and for that it needs to have the respective tolerance on the surface. So today we will be looking into a slightly different aspect, which is about what are the different kind of classifications of the patterns which can be made in casting processes. So principally there are about 6 different types of patterns which are available. One is called the loose pattern, the gated pattern, and the match plate pattern, the cope and rack pattern, sweep pattern, and skeleton pattern. Now these are only the kind of patterning techniques available for a variety of different shapes that you want to cast, and some of the limitations are posed by the shapes itself, because of which this varied number of patterns exist. For example, let us say when we talk about a loose piece pattern, it is usually one piece out of the remaining part of the pattern which if you want to retrieve from the mold may create a mold damage. So you have to somehow bolt this piece to the main assembly and then remove the main pattern first, and then before removing the main pattern you unbolt the loose piece so that the loose piece still stays into the sand mold, and first extract the main pattern and then the unbolted loose piece separately, so that this way the mold does not get damaged, and therefore it is a very good technique to do single piece patterning. So usually these are made of wood, and you can use these for castings of large numbers. Then let us talk about gated pattern. Similarly to it's like a concept of high production, where let us say there are many molds which you want to fill with a single inlet channel. So what you do is that you make this inlet channel behave like a gate, with runners running from the gate in both the directions into different molds, so that therefore you have the gates and runners all sort of or many runners attached to a gate which is feeding from the pouring basin, and the riser can be on the other side of that main runner. So it is something like a network of runners. Let me just show you here what I mean by what I am saying actually. Let us say these are patterns which you want to fill up all at one go with the metal. So basically you make runners out of these patterns and connect all of them using a feeding channel or feeding runner, and you can have either a gate or either a riser in this direction or any other direction, for example in the single pattern. So basically the idea is that the filling of this cavity would be illustrated by the liquid metal flowing in this direction all the way to this direction and coming up or oozing out from here, which can give you an essence of the whole molding has been filled. So these are gated patterns. To typically one or more than one loose pattern with attached gates and runners provides a channel through which the molten metal can flow from the pouring sprue to the mold cavity. The pattern is frequently set on a follow board, so which can conform to the parting surface of the mold, which also helps in easy removal of the pattern after the mold has been prepared. Then you have match plate patterns. In the match plate pattern, the pattern is made into two halves. mounted on both sides of a match plate of wood or metal conforming to the contour of the parting surface. Now, typically you can also use a core here. So, what happens is that there is one wooden pattern that you have made and split it up into exactly two parts. If there is a core on it, there has to be also a core built up separately, which can also be done by this matching plate concept, that there are two, let us say, wooden black blocks on which you have developed the core separately using sand and sodium silicate. Okay. So, you can actually use the core as well as the cast by realizing the two halves of the whole pattern, one on the cope half, another on the drag half, and bolting them in a way so that they align to each other with a common board in between or a common small sheet in between, which is known as the match plate. Okay. So, once these two upper halves and lower halves are separated, the plate is removed obviously. So, you have the inverted geometry or the negative geometry of whatever pattern is there on the match board, and you can place a core and then close on the cope half and the drag half together by removing the match plate. So, that now you have a cavity with the core. Okay. So, this is actually a match plate pattern. It's a, you can have a match plate in a typically for small castings where you have more than one components on the pattern. So, basically supposing there is a continued part where there are different features, some of them are in the cope half, some of them are in the drag half, even that kind of a realization can be done using the match plate patterns. Then there are cope and drag patterns. Here the cope and drag halves of split patterns are separately mounted on the two match plates. So, you are doing, instead of one match plate, two different match plates. One match plate goes into the cope half, another match plate goes into the drag half, and you have ensured that the match plate has been fabricated in a manner so that it has exact one to one synergy of the components on the half patterns on both sides of the matching plate. So, all it needs is to sort of match the upper half of the plate with the lower half of the plate, and then cast and then remove the plates, so that there is a cavity which is formulated. So, the difference between a match plate pattern and a cope and drag pattern typically is that a match plate has a single match plate, and in a cope and drag there are two different match plates with different split patterns which you are recombining together. Then there is a sweep pattern, which are normally again made of wood to generate surfaces which typically induce revolution, surfaces of revolution. So, basically there is, let us say, a radius, and there is a certain shape of this particular radius, and as the molder moves the radius in a circle around a central point which is fixed, you will actually have a pattern generated by the shape in a circular basis. Okay. And so, it is very easy for particularly large casting processes. So, you can have you can also sweep, because you are sweeping the radius, so you can refer to as sweep pattern, and it refers to the section that rotates about an edge to yield a circular section, etc. So, it is normally preferred on sort of geometries which are very, very large. Then you have a skeletal pattern, which consists of simple wooden frame outlining the shape of the casting. It is used to guide the molder for hand shaping the mold for large castings having simple geometric shapes. So, you can actually go into the skeletal, it is not one single pattern, okay, and then try to hand shape by putting the sand around the skeletal, so that you can exactly have the the skeletal replicated using casting process. So, these are generally the 6 different types of patterns, and then coming to just a look of what are the considerations. So, while designing a pattern, the parting line should be chosen so as to have the smallest portion of the pattern in the cope side. Obviously, because when you are trying to put liquid metal inside the cast, there is also going to be a factor of buoyancy, and this buoyancy would ensure that if supposing a major portion of the metal goes into the cope half, which is the upper half, there is a possibility of the mold to be damaged or disturbed because of the huge buoyant forces which would result. Rather, it is preferable that you have the drag half, the lower half as most of the metal containing containment, and the remaining metal, whatever is left over, even a small part could be in the cope half. So, normally the patterns are not realized into 50-50% in the cope and drag half, but obviously the smaller part is in the cope half and the larger part is in the drag half. So, as the molding sand has greater strength in compression than in tension, the heavier sections of the pattern should be included in drag. Okay. Obviously, you are trying to keep the sand intact, so that there is no damage and the casting can be formulated easily. These are some of the details. This is a wheel pattern. As you can see, this is again a split pattern of this wheel that you wanted to cast. So, you can have a cope half and a drag half, this is the cope half, okay. This goes into the drag half, and so this is how you typically make these split patterns. So, let us now look at the type of molds just as the type of patterns. So, molds can be classified on the basis of the material that is being used. For example, there are green sand molds, there are plastic molds, metal molds, and also on the basis of the method for making them. Like for example, you have the shell molding technique or the investment molding technique. So, we will delve into some of these. So, metal molds are permanent in the sense that a large number of castings can be made from a single mold. On the other hand, the molds of refractory materials can be used only once, because you have to reclaim the sand once the casting process is over. In fact, I told you that there is a reclamation process associated with all casting in the first few lectures. So, generally the green sand molds are used, which we will discuss in details now. So, green sand mold, what it composes of? Material of a green sand mold typically is a mixture of sand, clay and water, and some organic additives, normally wood flour, dextrin or sea coal. And the way that it goes is that the organic additives get vaporized, okay, and it always creates a good porosity and always creates the refractory sand to have some scope for expansion without breakage. Because think of it that the sand grains are put together in the assembly like a bunch of different balls, and there are these small organics inside which get vaporized. So, there are going to be cavities created where if the sand expands, there is enough space for it to go. So, the mold will not be broken because of the expansion of the sand as such. So, that is the reason why these organic additives are very, very important. Percentage of these ingredients on the weight basis are approximately 70 to 85% sand, about 10 to 20% clay. This is used mostly as a binder material, and about 3 to 6% water and about 1 to 6% adhesive. The ratio obviously may vary depending on whether the casting is a ferrous casting or a non-ferrous casting. And typically that the most inexpensively available material which is a refractory material and which can hold strength at a higher temperature is sand. But the problem with sand is that sand standalone cannot formulate the desirable properties that the mold must have, and therefore, this has to be sort of mixed with clay and water and other ingredients as mentioned, and this makes the whole mix which is used for casting processes quite expensive. Okay. So, normally it is a higher clay content than desired, and so sand also has to be cleaned in a way to make pure sand. Okay. So, this includes the processing cost. So, let us talk about now what are the different aspects of the green sand mold. So, I think I have already mentioned about the specified quantity of clay, and the naturally available clay content may be more, but you have to somehow cleanse the sand of the clay by washing it. Then you have water additive content. In addition, it must have a specified grain size distribution. This is another very challenging issue, because obviously if it has a wide grain size distribution, it may result in a lower porosity in comparison to if it has a similar kind of grain size. So, think about it that if supposing the sizes of the grains are almost equal, and I am also further saying that they are spherical in shape, and you are going to pack these grains together. So, obviously the bulk density would be quite low, because these gaps would be very high, okay, because you are all spherical grains, like it is a pack of spherical balls put together in an assembly. So, obviously there is going to be a huge amount of porosity inside, and the density would go down. So, the bulk density of the sand mix generally in that case is very low if the grains are of almost equal size with smooth round shape. On the other hand, if the grains were angular, and then it had different shapes, then obviously there would be all these voids filled up, and the overall bulk density would be very high in that event. and the porosity would be low, which is not a desirable condition for doing castings. So, our preference here would be that if the sand grains are all spherical and have uniform size, then we will have a better situation. Obviously, I have no need to reiterate that at a higher temperature the sand expands and it looks at those voids where it can get into without breaking the mold. So, you are giving porosity just for that purpose, and you are actually creating it using some kind of additives etcetera, which vaporize and create these pores. So, that there is no problem of the sand expanding and breaking the mold as such. So, such grains result in an increased void and higher permeability, and obviously higher permeability permits easy outflow of the gases, which may otherwise be entrapped within the casting as well, apart from the strength issue that I was mentioning. And if you have various sizes and have sharp corners of the grains, so then the gas cannot come out so easily, and also it cannot accommodate the expansion of the sand, which makes it having a lesser strength overall. So, how do you actually do the separation, size based separation of the sand grains? So, you pass it through sieving matrices of different dimensions and collect different grains, so that you can actually categorize a grain as some grit size, okay, or below some grit size, and this you can plot by seeing that how much of these grains are so basically all grains of a higher size than the grit size would be retained vis-a-vis all the grains of a lower grit size, lower size than the grit size would actually pass through the particular sieve. Okay. So, it is a lot of a sort of a filtration system, where you can actually plot what is the quantity of the grain size 1, grain size 2, grain size 3, so on and so forth. Okay. So, the amount of sand that collects in the different sieves is plotted, okay, and finally, this plot gives you the grain size distribution with the average grain size as well as a spread around which the grain size varies. So, as I already told you, the clay together with water acts as a bonding agent, it imparts tensile and shear strength to the molding sand, and the organic additives burn out at high temperatures and make room for the molding sand to expand and saves the mold from crumbling. So, these are some of the issues that I have already discussed. And so, in regarding green sands, again the success of the casting process would typically depend on the properties of the molding sand. For example, this must include high strength, more permeability, so that the gases can outflow of the casting, more deformability and flowability, because obviously the sand needs to get into intricate shapes etcetera, particularly in complex castings to formulate the boundary and make the cavity. So, it has to be good, it has to have good flow, and then it should have a good refractoriness and should be able to hold strength at a higher temperature. So, these are the 5 essential characteristics that would be there in a sand molding sand. So, the strength actually mostly refers to the compressive strength as far as the casting process goes. Obviously, the metal is going to formulate, it's going to be on the top of the sand and exercise a weight on the sand, which will make it more and even if it is a, let us say if it is inside a sand cavity, its buoyancy forces would actually also make the sand compress on the other side of the wall. So, it is essentially compressive strength that we are talking about in all casting processes, and the deformation indicates the change in length of a standard specimen at the point of failure. Okay. So, that is how strength can be gauged. Strength of a material can be gauged by looking at the maximum deformation that would be allowed without failure, without the sand getting failed. And so, the other concept which is important is permeability. It is expressed as a gas outflow rate through the specimen under a specified pressure difference. So, it definitely includes the quantity or density of voids and also the void sizes of the particular mold. The other important ability is the flowability, obviously refers to the ability of a sand to flow around and over the pattern when the mold is rammed, and the refractoriness measures the ability of the sand to remain solid as a function of temperature. So, I think I have covered all these 4 parts as I mentioned earlier. The most important part that I would like to illustrate is that this factor permeability, and in fact as a matter of fact all the other factors, strength, deformation, flowability, they are dependent on the percentage water content that the green sand mold would have. And let us look at how the permeability would vary. So, obviously, if the water content is quite low, then there is a situation that the loose clay which is available, it can actually, it is a very small size particle, and these can get into the, it is like a dry clay powder, it can get into the voids, and because the water is not there simply, or adequate water is not there simply to formulate a bond and hold them together. So, they are all loose particles. So, at a lower amount of water mixed into the particular sand, there is a tendency that the dry powder may get into the voids etc. of the sand mold. So, obviously, the void would all be filled up and the permeability would be lower because of that. Now, as the water content is slowly increased, there is a point of time when water is just about adequate for the clay particles to sort of go and coat all the sand particles together. So, now there is a bond formulation between the silicate which is there and the the clay particles, and so in that situation you can say that all the loose clay which was otherwise powder into the voids have been taken up and coated onto the sand particles, mostly spherical, and so still it releases a lot of voids which were otherwise filled with this loose powder now. Okay. So, the permeability would go quite high in that particular case, as you can see from here to here, as the percentage of water is increased between 2 and 8%. Now, what happens after that is that essentially now all the clay is gone because it is coating the particles, the sand particles, but if you put water more in this situation, then all the additional water comes back into the voids and fills the void, so that the permeability can go down. So, that is how you can see a depth or a decrease in the permeability with an increased content over and above 8% water into the sand mold. So, this is a very important aspect, and similarly explanations are available in the literature all about flowability, deformation, strength, as this concept of loose powder clay, coated powder clay, and additional water into the different voids of the sand mold. So, with this I think I would like to, in the interest of time, end up this particular module, and in the next module I am going to again continue some of the issues related to again how to prepare these molds, what can be a high yield process for making mold at a faster rate like jolt ramming etc., some techniques, and we will also talk about the basics of how there are challenges related to dissolution of gases into these liquid metals, and how that can downplay the quality of the cast, and also look into some aspects related to how you melt those metals and ensure that there is very less amount of undesirable gas dissolution. So, with this I would like to close on. Thank you.